In this module, we'll be talking about feature encoding. So we'll begin with what is feature encoding, why to perform feature encoding, choosing the appropriate feature encoding, and then common mistakes to be avoided. And we'll particularly emphasize on this piece because if you go wrong with the encoding, it could really affect the results at the end. Finally, after understanding all this, we'll be doing the hands-on exercise in Python, where we'll be applying all the encoding techniques that we have learned on a dataset in Python. What is feature encoding? Conversion of categorical data or non-numeric data into numerical format, primarily for providing input to the machine learning algorithms, is called feature encoding. So let's say we have two tables here. The table on the left represents the categorical data. For example, you may subscribe to an OTT app where you may have favorite shows that you watch. Now, these shows could come from different genres. For example, you may be liking action, your friend likes comedy, and someone else likes sci-fi. Likewise, when you go to an e-retail website to make purchases, you may have favorite categories to browse through. For example, somebody might be interested in books, someone else might be interested in furniture, and they could be people who are very much interested in the electronics and the latest gadgets. Likewise, there could be a column in the data which talks about ratings, and these could be good, average, and poor. So if you see, there is a general format that these variables on the left follow. They all have string entries, which are not directly numbers. So directly adding, subtracting these categories or performing arithmetic operations here won't be feasible. So we'll have to bring them to some numerical format before we give them as input to our models. And we'll discuss that. However, one more point that you want to be clear about, there could be such columns where there is no order. For example, your preference might be that you like action movies and someone else likes comedy movies. You can't say action is greater than comedy or comedy is better than action. It's a personal choice. Similarly, the categories of items that you want to browse through on a website can't have an order. If you like books, that's your preference. Someone else might be interested in electronics, and that's that individual's preference. You don't have an order here necessarily. But when it comes to ratings, you know this tends to give a sense of order. When you're saying something is good versus an average versus a poor, there is a sense of order here. So the categorical variables could be nominal when there is no sense of order, or ordinal where there is an order. On the right, we have a very interpretable table, which is a collection of numbers. So we could be talking about time. We could be talking about a score obtained out of 100. We could be talking about distance from one place to another. All these places we have numbers, and these numbers could be rounded off integers or could also be floating points, which may contain decimals. But end of the day, these are numbers, and we can meaningfully perform all arithmetic operations on these numbers. Let's now discuss why to perform feature encoding. Once again, so feature encoding is essential to prepare categorical data for machine learning, ensuring that it can be correctly interpreted by algorithms. It allows the model to extract valuable information contained in categorical variables while performing both supervised and unsupervised tasks. Whether you're talking about predicting an outcome or you're talking about studying patterns in the data, encoding becomes very, very important. Just on the previous slide, we discussed ratings as good, fair, and average. Now, there is no way that a model will be able to figure out this sense of order unless we supply it that way. Similarly, if there's a column which does not have an order and we try to bring it, that is again not going to be good. So we'll discuss this at length as we proceed. For now, just keep in mind that this is essential for our models to be given the right input. Choosing the appropriate feature encoding. Now, there are a couple of choices here. For example, we can perform something that's known as label encoding. We can perform one-hot encoding. We can perform ordinal encoding, custom encoding, or target encoding. This is not an exhaustive list. We can have at least 10 more different types of encodings, but the bottom line is, if you know these many, you'll be sorted for more than 95% of the cases. Let's discuss each of these one by one. Coming to label encoding. First of all, label encoding is supposed to be used only for target variable. So if you're doing a predictive modeling task and your target column is categorical in nature, that's only when the label encoding is applicable. It converts the categories into numbers as per the alphabetical order. That's, again, an important point. It doesn't really rely on any other order, but goes by the alphabetical order. To look at an example, let's say we have a column, which is our target column. So a bank is interested in profiling the type of loan that's most appropriate for them to pitch to their prospects. So somebody who's an existing customer could be eligible for a home loan. Someone else could be eligible for a personal loan. We are deciding which is the most appropriate type of loan to be offered to a given prospect. Now, this kind of column that you're predicting could have these labels like home, personal, auto. Some other customer has home as a preferred option and auto. There could be more data, but we're just showing you first 5 rows. Now, if we apply label encoding on this, what will happen is it'll assign an alphabetical order. So alphabetically, A comes first. You'll get a 0 for that. Then comes H, which is for home. So you get 1 wherever home was the preferred choice. And finally, P in the alphabetical order would be the last. So that would be given a value of 2. It's kind of starting from the lowest to the highest alphabetical order. That's how the encoding is done. Now, this is totally acceptable for a target column because in the target column, these all will be seen as different categories. And we retain this information in one column. Keep this in mind, label encoder is used only for the target column. In fact, label is just another name for the dependent variable in machine learning lingo. That's how we normally call it. Moving on to the next, one-hot encoding. Now, all these other encodings that I'm going to talk about are primarily applicable for the independent variables, the features which are explaining an outcome, or maybe just the features in case of an unsupervised learning where you are studying the patterns in the data. So one-hot encoding is used when categories within a column cannot be assigned in order. There is no order that exists. Each category is equally important. To look at an example, you may look at the same genre example. So we can't say that somebody's preference, that's action, is less important compared to somebody's preference that's comedy, or the other way. Or sci-fi is better than action and comedy. We don't have a sense of order. It's an individual's preference. So in a data set, this might be one of the columns which is talking about an individual's preference. Whether this person prefers action, comedy, or sci-fi, these are the choices may be given, and this person has chosen one. Another person has chosen comedy, the next person has chosen sci-fi, so on and so forth. Now in this case, since we cannot give an order, giving equal importance to each category is important. How do we do that? We create 3 new columns for the 3 categories that we had in the genre column. Now, in order to fill these columns, we follow a simple rule. So wherever in our data we had action, these 2 places, in the action column here, we'll have to put a 1, and the remaining places will be filled as 0. Likewise, wherever in our data we had comedy, these 2 places, we'll put this as 1, and the remaining places will be filled with zeros. Likewise, wherever in our data we had sci-fi, we'll put that as 1, and the remaining places will be put as zeros. So eventually, if you apply it on all the columns, this is how your data would look like. Notice that the sum of each row in this case is 1, because in our case, we just looked at one genre for a given viewer. Now, if we realize there is some information that's a bit redundant here. If we know any 2 features of the 3, can we derive the third one? Let's say, for example, we blindfold the action piece. Now, can we guess where action would have been a 1? In the first case, if it's not comedy, it's not sci-fi, and we only have 3 categories as possibilities, it must have been action. Similarly, in this case, when it's not comedy, not sci-fi, it must have been action. How about this case? When it's already known to be comedy and it's not sci-fi, it cannot be action because it's already known to be comedy. Likewise, for the last row, if you see, it's already known to be comedy, it's not sci-fi, so it has to be a 0 for action as well. Similarly, in this case, it's not comedy, but it's known to be sci-fi. If that's the case, then it cannot be action. So action again will have to be 0. So in a way, in such cases, when you do one-hot encoding, if you have n categories in a column and you create n new columns, you don't need n columns. You can figure out the nth column by using the n-1 columns. Generally, we drop the first feature there. So this is a practice. This is also called dummy variable encoding. So we are kind of converting a categorical column into these dummy variables. And there's a concept of a dummy variable trap, basically, which indicates that we may not need to use all the features that we've derived. We can manage with n-1 features. If we had n categories, n-1 columns would capture the necessary information. And we are not losing that information because it's automatically implied. This is called one-hot encoding. Now, there could be times when we actually have an order in the features, like some kind of ratings, and we want to retain that order. For example, let's say we have these kind of ratings in a column, which capture ratings anywhere from poor to excellent, everything else in between. Now, in this case, if we do one-hot encoding, it may not be a fair idea because it'll lose a sense of order. So how to deal with such scenarios where we want to maintain a sense of order? We may want to give an order as per the rating. And there are ways, we'll discuss this in the hands-on piece. In Python, generally the indexing starts from 0, so you can give it ratings from 0 to 4 because we have 5 levels, so 0 to 4 would suffice. This is called an ordinal encoding. An extension of ordinal encoding could be a custom encoding. Custom encoding would be applicable when you don't want to go linearly. For example, you don't want to call it 0, 1, and 2. Maybe you know that high, in case of, let's say you're doing a credit risk assessment, high has much greater impact compared to medium and low. With your subject matter knowledge, have relative weightages for these. And how do you assign that? That's something which could be done through a custom encoding. Ordinal encoding would always go in a linear way, 0, 1, and 2. Custom encoding could be allowing me to say that high is 3 times more severe compared to medium, and medium is 3 times more compared to low. This is a very custom weightage that we have given here. We use this encoding when a column follows an order, but the order needs to be weighted in a custom way. Now moving to the last encoding that we're going to cover, it is known as the target encoding. It is used to transform categorical variable based on the mean or some central tendency of the target variable. What is a target variable? The dependent variable or the label. Generally preferred when the categorical variable has very high cardinality, which means there are too many categories. In such cases, we prefer to apply target encoding. And we'll discuss more on this as we go to the hands-on piece. So let's look at an example of target encoding. We are trying to predict sales, and one of the features that we are trying to encode is state. Now, state has 50 categories. So would you get 50 different columns in your data? 50 minus 1 would be, n minus 1 would be 49 in this case, but 49 columns could be a lot of columns to deal with at once. So in such cases, compared to one-hot encoding, we would prefer performing a target encoding. In the hands-on piece, we'll also show you multiple ways to deal with such scenarios, which is a common occurrence in most of the data sets. Let's take a better example of target encoding. Let's say we have some data related to an individual's preferred genre, the plan or the subscription. The OTT services generally come with multiple options. How many devices do you want access to and things like that. And then there is a prediction that's being made on whether a customer would renew the subscription or not. So 1 means the subscription would be renewed and 0 means the subscription would not be renewed. So in this case, when we talk about encoding, we don't have to worry about the plan feature. Why? Because this is already numeric. We'll instead have to worry about the column called genre. And when we come to a list of genres, you can come up with a list of 20 odd genres as well. How do you actually go ahead and encode? Let's look at this with the help of this simple example where you only have 3 categories right now. How do you go about doing that? So first of all, it would require us to calculate some probabilities. So if we are asked, can we find out the probability of renewal given that the person follows action genre? So which means we are focusing on only the records which belong to action genre. In whatever data is visible to us, there are 3 such instances of action genre being a preferred genre, out of which 2 times the renewal has happened. So can we say the probability of this is going to be 2 by 3, right? And likewise, can we look at the overall probability or global probability of renewal, assuming that we have only just this much data? So we will only be looking at the renewal column now, and you can see out of 6 instances, 3 times the subscription has been renewed. So the overall probability of renewal is 3 by 6, 3 times out of total 6 times. Now, target encoding is an elaborate concept, but to tell you in a nutshell, it uses a blended probability. It gives a relative weightage to the genre or the category, and it gives a weightage to the average belonging to the global scenario. And this is a weighted average kind of a concept. So where you have W1 times the probability of renewal given a genre plus the global mean or global average with a certain weightage, and you're dividing it by its total. This is done to ensure that for those records which have minimal occurrences, for example, sci-fi in our data just occurs once, we do not make wrong decisions. As per this, looks like that if somebody has sci-fi as the preferred genre, this person will never renew. But would that be the case? We have very limited representation of sci-fi here. So in those cases also, when we calculate the blended probability, we will be able to find out some weightage for sci-fi given the overall app. Will not be just overshadowed by the limited occurrences of sci-fi. Plus, there is a problem known as the data leakage. To avoid that, target encoding has some built-in intelligence, but we'll talk about it at the appropriate stage. Now let's move on to the common mistakes to be avoided. In a way, you already got a hint related to that. So let's say if we use these encodings interchangeably, will that be wrong? For example, let's say we use ordinal encoding in place of one-hot encoding. We introduce an order when there is none. Same example, genre. If we start giving it an ordinal encoding, which is something based on the alphabetical order maybe, we'll say action will always be given 0 because A comes first, then comes C as in comedy, so you'll give it 1, and sci-fi comes last, so you'll give it 2. But are we not in a way suggesting the machine learning algorithms that sci-fi is carrying a lot of weightage compared to action? And is there actually any such comparison we can do? Not really. So this would be wrong input to the model. What if we do it the other way? For example, if we use one-hot encoding in place of ordinal encoding. So you had these kind of ratings, good, average, and poor, and you start giving them all equal importance. Are you not hiding information from the algorithm by doing this? Because right now, the way you've given this input is suggesting the algorithm that good, average, and poor are all equally important. So changing the encoding types would lead your model to suffer. Why? Because it would not get the right intelligence in the form of inputs. Our machine learning models will struggle to make sense out of these variables if the encoding is not right. So it's very, very important to give the right encoding. In my experience, I've seen examples where people have encoded months of a calendar year from January to December in an order from 1 to 12. That suggests that December is always going to be 12-fold more compared to January. And if you bring it to the right order, if you say that all the months are equally important, the things are very different. In a regression problem, the R-square value jumped from a 42% to an 84% by just choosing the right encoding, not giving an order when there is none present. With this, we come to an end of the theory piece. We'll do the hands-on in the next video, and that'll be a detailed hands-on covering each type of encoding that we have theoretically introduced here. You will get complete understanding of how to apply it. We are at the Google Collaborate tree, and I've already pointed to the data source, which is called healthinsurance.csv. This is the data set we are going to work on. We begin by calling all the basic libraries like NumPy, Pandas, Matplotlib, and Seaborn, and suppressing the warnings because we don't like to see those unpleasant messages. Once these libraries have been loaded, we are calling the data frame through Pandas read CSV. This data set is about health insurance. So the background is that the insurance company, that's our client, they already have some existing customers who purchased an auto insurance from them, which is essentially for their cars. Now this company is looking forward to pitch a health insurance to these people. So they already know these customers. They have relevant information related to these customers, but they're trying to pitch another product to them. We'll see what kind of features we have in this data. Let's first read the data. It's a small data set. We have about 10 features and 500 rows in this data. You check the shape. If we check the data types right now, we have a mix of data types. Majority of the features in this case are object type features, and there are two numerical features, age and income. Now, we can apply encoding only on the categorical variables, and we seem to have plenty of these. Why? Because we will be trying all different types of encodings here on different variables. Please note your data frame doesn't have to have just one type of encoding. Different type of features demand different types of encoding. Let's just randomly sample 5 observations from the data overall, just to get a glimpse of how does the data look like. So if you see, these are the features that we have starting from gender, education, age, income, region, employment status, marital status, credit rating, car brand, because they already have an auto loan, and target column, which talks about whether this customer who already is an existing customer for the auto insurance has also subscribed or purchased a health insurance from this company or not. So in some cases, it's a yes, some cases it's a no. Now let's just glance through the features and understand their nature. Gender, what kind of feature it is, we can't have an order here. Education, you can imagine it would have an order. So it may have a sense of order. When somebody says this person has a master's level education, it's greater than the bachelor's level education, right? So you may want to bring a sense of order. Age and income are non-categorical variables. They're numerical, self-interpreted. Region, again, we may not necessarily want to assign an order unless we have a reason to believe so. Employment status, again, we don't know a specific order. Marital status, once again, we cannot give an order. Credit rating definitely comes with an order. When we say somebody has an excellent credit rating, that means it's better than the good, and that in turn is better than fair, right? So we have multiple options here. Car brand, there are different car brands that we see, and all these entries so far, at least in the 5 randomly sampled records, look different. So we may have more categories. Of course, we can't say there is a specific order here because we don't know how old that car is. An old luxury car might be at par with a brand new mid-range car in terms of pricing or insurance pricing. So we can't really build an order here. And the last column here is the target column. So we begin by working on the label encoder. We'll go in the same order in which we discussed it in the theory. Label encoder, as stated, will be applied only on the target column. So from sklearn, scikit-learn preprocessing, we are calling the label encoder class. It has to be instantiated like this. And then we are saying to the target column, do a fit transform, restore it back as the target column. So we are overriding the existing target column. If you see right now, it says yes and no. And when we do a fit transform of this label encoder on this, once again, when we check the head, what happens? It converts this into 0 and 1. Notice this is an alphabetical order. When we say yes and no, no alphabetically comes first. So that gets a 0, and yes comes later. So that gets a 1. That's how we encode it. So target column is sorted. This is how these 2 categories would be identified. Now coming to the features which deserve one-hot encoding. And let's look at some of these features. Gender, region, employment status, marital status, and car brand. We are saying we don't have a sense of order here to begin with. Education has a sense of order, and credit rating has a sense of order. So we are not mixing these. We are trying to deal with those features which do not have a sense of order. And only those features are subjected to one-hot encoding. We are doing a small check here for all these features, which are supposedly nominal features, which means they don't have an order. We are saying we'll run a loop over them to look at the name of the feature and how many unique categories are present. For example, gender could have male, female, and others, or maybe just male and female. For example, employment status could have 4 or 5 different categories. So we are just checking how many unique categories are present, and we are doing a value count on that feature. So for I in nominal categorical variables, I would be each feature one at a time. Starting from gender to car brand, this loop is going to do that iteratively. And then finally leaving a space between what we print. So let's just check this. So you can see gender has 2 levels. In our overall data, we have 267 males and 233 females. Region has 4 levels or 4 categories, and this is how the categories are distributed, so on and so forth. Everything else is okay. We have 2, 3, 4 categories, but the column called car brand here has 30 categories. And this is how the numbers are. So this is a synthetic data. It's not a real data. And that's why these numbers are very similar at places. But you get an idea. This is how we're supposed to work on such features. This has too many categories. Would this be the right candidate for one-hot encoding? Because one-hot encoding creates those many new columns. So if we have 30 categories, we'll create 30 minus 1, n minus 1 new columns, which is going to be 29 new columns. On a data set which originally had only 10 features, might not be very wise to do that. So let's deal with the rest of the columns first and see what we can do. And I'm going to show you 2 ways to do one-hot encoding. First is using the scikit-learn's one-hot encoder. The other is Panda's get dummies option. Let's do the one-hot encoder bit first, and then I'll show you get dummies. I personally would recommend that you try get dummies because it saves you certain lines of code. Let's make a copy of the data frame. So far, we have just handled the target column, which is through the label encoder. So we are making a copy of the data frame, and we are instantiating the one-hot encoder class. Now, when you apply one-hot encoder, the output that it generates is in the form of a sparse matrix. Sparse means it will have a lot of zeros. We don't want that. So we are setting that to false because when we do this, the output would be in the form of an array, NumPy array, which is very easy for us to handle. And then we are dropping one of the categories. This is being done just for that n minus 1 thing. So if you have n columns, we will be able to manage with just n minus 1 features as explained in the theory video. Let's take these columns, not the one which is car brand because it had 30 plus categories. We've taken the other 4 columns here that we are going to apply one-hot encoding to. So one-hot encoder, fit transform on what columns? These columns. So when I say df1 and the list of these features, it's going to select only these features from the overall data set. We are not changing the rest of the data. We are only selectively working on the columns that deserve this one-hot encoding. Finally, when you do a fit transform, like I said, the output would be in the form of an array, and we want to store it back as a data frame. So we are saying these will be our encoded columns, and we are giving it the names as per the original data. For that, we have something called as get feature names out. So this selectively shows the names of those features which are being subjected to encoding. This is the purpose of this entire input here. Finally, we will concatenate the encoded columns of data frame 1 to the original data frame, and the columns that were originally in the form of strings will have to be now dropped. We don't need both. If we have encoded it, we simply need to drop the original column. So this much effort needs to be put here. First, you select the features separately, you do encoding, then you concatenate, then you drop the original features. This much is the effort needed through one-hot encoder, and which is the reason why I said you may prefer get dummies, which is what I'm going to show you next. But let's run this now. And you can see gender column for that matter had 2 categories, male and female. Since we dropped one of the categories, we only left with male, and it'll have a 1 wherever the gender in the original data was male and 0 otherwise when it was a female. Region-wise, we had 4 regions, north, east, west, south. One of the regions has been dropped, and the remaining 3 regions are visible to us. So on and so forth for the employment column and the marital status column. This has created new features. So if we look at the shape of the data frame before encoding, that was df. If we check the shape of the data frame, just particularly the columns, we had 10 features to begin with. Now, if we check the shape of the data frame after one-hot encoding, that number would have increased. And that's something which we can check here by simply adding df1.shape1. Let's run this, because we made a copy of the data frame, right? See, it has 14 features now. The number of features have gone up. Let's understand how do we come to this count of 14 now. Our original data frame had 10 features. How many new features will be added as a result of this one-hot encoding? N minus 1. So how many categories are there? 2. 2 minus 1 is going to be 1. How many new features will be added for result? It will be 4 minus 1. That will be 3. How many new features for employment status? 3 minus 1. That is 2. How many new features for marital status? Again, 3 minus 1. That is 2. Because we dropped the first category. So how many new columns we got in our data set? 10 plus 1 plus 3 plus 2 plus 2. If you check, that comes out to 18. But the output we saw was 14. Why? Because we dropped the original representation of all these 4 features. You also had a column which stated string-wise male, female, north, east, west, south, the original representation of these 4 columns, which have now been one-hot encoded, will again be dropped. So effectively what you have is 18 minus 4, that's 14. And that's the number of features that you can see here. Now, you saw this one-hot encoder and its application, 4 or 5 different steps involved. Why did I say it may not be the best choice? The reason for that is that there's a straightforward method in Pandas itself, which is called getDummies. And this is just one line of code. What you have to do is you have to point to the specific data frame. I'm working on the original data DF only. You have to point it to the columns that you want one-hot encoding to be applied to, and you do drop first is equal to true. So in this one line of code, you're pretty much making those changes in place rather than taking that data separately, applying one-hot encoder, concatenating it back, and then dropping the features manually. If this saves time for you, it's your preference. You can apply one-hot encoding directly like this. You have gender column as male, you have region column with 3 categories, employment column with 2 categories, and marital status again with 2 categories, n-1. The same thing applied in a straightforward way. Notice earlier when I did this, I created a copy of the data frame where I applied it through one-hot encoder. Because I preferred this approach, I'm working directly on the original data frame here. And once again, if you check the shape of the outcome, it has 14 features. We started with 10 and now we have 14 features. Now remember, there was a column called car brand, which had too many levels, 30 levels to be precise. We could not apply one-hot encoding there, fearing that it'll add too many columns, 29 columns, n-1. Can we do something about it? So just showing you a treatment for that, and I'll show you an alternative way as well. Let's make a copy of the data frame at this stage. So right now we have 14 columns. That's our data frame. So just making a copy of the data frame at the current stage. We are looking at a count plot where we'll be looking at the car brand column of the data frame 2, which is a copy, and we'll be sorting the bars that we get in the count plot in a descending order of counts. Applying a rotation on the x-axis so that we can read the x-axis labels properly. When you have too many elements written on x-axis, there would be a clutter. Finally, we are calculating the value counts, which means for each car, how many occurrences are there. So we are capturing it as an object called frequency. Let's run this. This is nothing but the output of value counts. In a way, we saw this here earlier, and we are looking at it graphically now. So there are some cars which have occurrences like they occur 40 times, 30 times, 20 times, and some cars have just 2 or 3 occurrences. We are looking at the same information through this plot. And this rotation of 90 degrees essentially makes sure that we are able to read these labels here. Otherwise, these would be horizontal by default and will not be easy to read. Now, what we are saying is that if there are certain categories of cars which are very limited in occurrences, why don't we club them into one? That would lead to a reduction in the number of overall categories present in the column. And we'll be able to focus on the categories which are more frequent, more popular, you can say. That's what we are trying to do. So in order to do this, we are saying we will only consider those cars which are occurring more than 25 times, which means anything that occurs less than 25 times, let's club it into one category. The less frequent cars will be clubbed into one category called others. So we've decided a threshold, which is a minimum threshold. And we are saying from this output of frequency, which is nothing but the value counts, we are filtering those categories which occur less than 25 times or the threshold times, and we are capturing their names. Dot index means their names. If you do just this much without index, it'll give you a filter on the value counts itself. When you do dot index on that, it'll give you the names of those categories, car brands, which occur less than 25 times. And finally, we are saying that in the car brand column, let's apply a dot replace method where we will keep those features which are to be clubbed, which have limited occurrences, essentially less than 25 times, and we'll replace them with other. And then we are checking how many unique labels or car brands we are left with now. So remember, we had this number as 30 earlier. When we run this code, what are we left with? 11 only. So that number 30 categories have been reduced to 11 categories. And now if you do a count plot of this, you'll see others as one category, which has too many other categories clubbed into it, but the original categories of important cars are visible. And others is something, while it may be a high count, you can still discard because these are not those frequent cars. These are the cars which are relatively less common. Now on this data frame 2, where we perform this change, we are applying getDummies as we did earlier. So what has happened? We had 14 features when we came to this stage. We will drop the original feature, which is the car brand in the earlier representation. And we got these 11 new features for the 11 brands that we have, including others. And 11 minus 1, in fact, because we get n-1 new column. So if you look at it effectively, 14 plus 11 minus 1, that'll make it 24. And if you drop the original feature, that number will be 23. Let's see, that's what we get. And here you see this number is 23. We have 23 features in our data set now. 10 new features have just been added owing to this representation of car brand. So So generally the rule of thumb is if you have a categorical variable with more than 15 or in certain cases 20 categories, you do not prefer one-hot encoding. Again, it depends on the size of data, but the common threshold that people follow in practice is if a categorical variable has more than 20 levels or 15 levels in some cases, they do not prefer applying one-hot encoding straight away. They try to club subcategories, which is what we've shown you here. If you want to check how our features are now, we can check just df2.columns. You can see these 10 new columns here have been added through the variable called card brand. Get Dummies smartly shows you the names that the original card brand feature had a category called Ford, and that appears here. Had a category called Honda, that appears here, so on and so forth. So this is one smart way of dealing with those categorical variables which have high cardinality, which have too many categories in them. Now let's move to ordinal encoding. Now in ordinal encoding, we want to get a sense of order. Let's talk about the variable called education. We had a variable called education, which had 4 levels of education: high school, bachelor's, master's, and PhDs. We want to apply ordinal encoding. So we have an ordinal encoder that's available in scikit-learn preprocessing. We are calling that. And this needs to be told in what order you want to put your categories. So this is not a random order. Give it from the smallest to the highest order that you want to give. High school would be the lowest, and PhD in our case would be the highest. This input needs to be given by us in the right order. That's what we've done. And then finally, we are doing fit transform on which column? The education column of the data frame. We are storing it as df encoded. And we are just checking for the time being the original column and the encoded column, first few observations, to see how does it look like. So if you see, if we give the order, this would get 0, this would get 1, this would get 2, and this would get 3. Is that what we have? So masters would have got a 2, high school would have got a 0, PhD is the highest category out of 4, so that'll get an index of 3. Bachelor's is the second after high school, so that gets a 1. This is how the order. Now that you've got it, you can always drop the original education column from the data frame because we have got a numeric representation for it. This is when you have used an ordinal encoder from scikit-learn, which essentially goes in a sequence as you supply, starting from the index 0 to the highest level. But what if we wanted to give a specific weightage? And for that, we've reserved a variable called credit rating in our data. Let's say we want to say that excellent needs to be given a rating or weightage of 10, good needs to be given a weightage of 7, fair needs to be given a weightage of 3, and poor needs to be given a weightage of 1. Now, this is not 0, 1, 2, and 3. We want a custom order because we may have some intelligence around it, and we want it to be seen like that. Excellent has to be many-fold more compared to, say, a fair. We just don't want to give a difference of 2 between them. So now, custom encoding is not something that we are applying through a library. We are simply taking the credit rating column and using a dot replace along with this dictionary. If you see, this custom encoding that we have defined is a dictionary structure. Key is the label as it appears in your original data, and this value here is as you want to represent it. So we just apply this dot replace method. It understands that wherever I encounter excellent, I have to replace that with a 10. Wherever I find good, I will have to change it to 7. That's it. And then we can quickly compare the original credit ratings with the credit ratings as encoded. Let's do this. So as you can see, poor got a 1, excellent got a 10 because that's how we defined it. We have a label called good here, which has got 7 here. Fair has got a 3, so on and so forth. This is how the ratings have been mapped. And once we've done that, we can drop this original credit rating column because we already got a custom representation for it. So this takes care of the custom encoding for us. Notice that we can also use custom encoding depending on our labels as we want to define them in place of ordinal encoding. We can just bring the right order and apply it. If you want to use it through scikit-learn library, however, you can do it that way. Now moving on to the last type of encoding, which is the target encoding. Remember, we talked about a blended kind of a probability calculation being done here based on the means and stuff. This is not straight away available through the scikit-learn library. In fact, it's there in a way, but it has a few glitches at the time when I'm recording this video. So I'm not using it from the scikit-learn library. If it gets resolved, maybe I'll create a separate video. But for now, we'll use it from the category encoders module. It's something that needs to be installed. It doesn't come there by default. So we'll have to install this, and then we can apply the category encoders. By the way, category encoders is a pretty rich library. It has at least 14 or 15 different types of encodings, but we don't necessarily need them all. So I'm just sticking to target encoding. Once this is done is when we can import the category encoders as C, just like we call NumPy as NP and so on and so forth. Within category encoders, we have a module called target encoder. That's what we need. And where do we want to apply target encoder? We want to apply this to the card brand column. Generally, you want to apply target encoder for features which have high cardinality. So I showed you an alternative earlier, which was reduce the categories, club them into others, and then solve it. The other way, or maybe at times a better way, would be a target encoder. So we are applying this to the column called car brand, and we are doing a fit transform, and we need to give it the input as the data frame and the target column in particular. So this needs to be told that this is the target column. We've already told the column with respect to which we are applying it, but it also needs to be told where is our target column. And then we can simply go ahead and rename the original car brand column with the car brand encoded. This is just to override the actual representation. Once we run this, you can see that there's a car brand encoded, which comes in these kind of numbers. And the original car brand has gone. So now if you see, looks like all the features are in the numerical representation. Remember, in the original data, we just had 2 features as integers and everything else was object. Let's see how is it now. So now you see original features, there were 2 integer features which are still there, but so many other features that we see are present here. So these are all numerical. These are floats, ints, and unsigned int, which is a little memory efficient way of assigning the integer representation to values which lie between 0 to 255. You can read more about this, but these have all been converted into numbers now. That's about the encoding. At this stage, your data would be pretty much ready to be given as an input to the model. Please note, there's one more aspect related to the train test split and all, but we've not touched upon it till now, and that's why I've not mentioned it here. That may be meaningful for people who already have experienced some amount of practical implementation of supervised learning. But for us right now, just understand the types of encoding which are applicable and when to apply what type of encoding.